Hello students, it's Professor Sansom. Today we're going to talk about some applications of nuclear chemistry. We'll review a little bit about radiocarbon dating and how that works, and then talk about biological effects and some applications in medical technology. So the first thing that I want to talk about is something called activity. Activity is just the rate of radioactive decay, and it tells you how many decays happen per second. So becquerels is the unit that we use, BQ, and it equals 1 decay per second. Sometimes we also talk about curies. If we have a large amount of radiation, we can use curies because it's sort of easier to deal with because becquerels tend to be quite large. And the way we find the activity is just K, which is our first order rate constant, times N, which is the number of atoms. And this is sort of analogous to the way that we talk about first order rate law. Rate equals K times the concentration. Here, activity equals K times the number of atoms. We do that because usually radioactive elements are metallic, and so they're not usually dissolved in solution, so it makes more sense to talk about the number of atoms. Okay. Eventually, we can put this all together, and we can get this equation that you'll see in the top right corner of your equation sheet. And the reason that we have A at time t and A at 0 is because those are talking about activities. You could also use concentrations if you wanted to, and it would work the same way. And then we have 1/2, and that's raised to the power t over t 1/2. T would be the amount of time that has passed since the sample, existed, I guess, in its original state, and then t 1/2 is the length of the half-life. So this equation is useful to us. We can use activities here. You can also do it with numbers of atoms directly if you wanted to do that. Basically, what are we going to use this for? If we know how much normally is there, how much is there now, and the half-life, we can figure out how old something is. And likewise, if we know any 3 of these 4 things, we can find the 4th. So radiocarbon dating happens because of carbon-14, which is a naturally occurring radioactive isotope. And the reason that it's useful for carbon dating is because the sun emits cosmic rays that will actually ultimately form carbon-14 in the atmosphere, which becomes incorporated in carbon dioxide. And carbon dioxide, of course, is absorbed by plants. They turn it into sugar. We end up eating the plants, and so as long as a plant or an animal is alive, it has a relatively constant amount of carbon-14 inside because it keeps getting it replenished from the food that it eats. But as soon as it dies, now the carbon-14 will start to decay and turn it into nitrogen-14. And when that happens, we can start to measure now the time that's passed since the death of that animal or plant. So we want to know what's the age of the archaeological sample. Go ahead and pause the video and work on this problem for a few minutes, and we'll come back together then. So to solve this problem, we're going to use the equation that we just saw, which is A at time t over A naught, our activity now versus our original activity, equals 1/2 times t over t 1/2. Now, we're looking for the age of the object, which means we want to solve for t. So I've just done some algebra here where I've solved for t. It's a little bit messy, but ultimately I'm going to plug my information from the problem into this equation to solve for the length of time since that tree died. So we have the log of the activity now over the original activity times the half-life divided by the log of 1/2, natural log of 1/2. And so we end up getting 2,280 years. Here is a quiz for you. So we'll go ahead and pause it again and submit your answers to this Podia quiz. Okay, so hopefully we figured out that we're solving for A at time t. and we got 13.2 decays per gram per minute. This is a little bit of a funky unit, but the units will be the same for the current activity as the original activity because they cancel out in the equation, so we can use that. Okay, that's everything with radiocarbon dating. Now we're going to talk a little bit about nuclear medicine and the ways that isotopes are used for medical treatment. So there are several isotopes that are commonly used in nuclear medicine, either for imaging or for treatment, and they can actually be manufactured or produced on site at the hospital. Depending on their half-life, it has to be on site because they don't last for long enough to be transported anywhere. So that reduces the number of places that can offer these kinds of treatments and imaging. But you can see here, for example, nitrogen bombarded with a proton can make carbon-11. We can also get oxygen-15 and fluorine-18. Each of those are or can be commonly used as PET or positron emission tomography in PET scans. Carbon-11 has a half-life of about 20 minutes, oxygen-15 is about 2 minutes, and fluorine-18 is about 2 hours. So it also varies how long they'll last to be able to make the thing that they're giving to patients and how long they'll persist within the patient's body. So let's talk about how positron emission tomography works. The way it happens is that a positron is emitted from a radioactive isotope, something that produces positrons, and it will collide with an electron. Now you may remember positrons are the antimatter equivalent of electrons, and it turns out when matter encounters antimatter, both things are annihilated, they disappear, and the entire mass of the positron and the electron that it collides with gets turned into gamma rays. So it's released as a gamma ray. And so in the PET scanner, the positron and the electron will hit each other, and they'll release gamma rays that go in opposite directions in this ring. And those are detected as bright spots. And then because they're detected in 2 places here in the ring, that allows them to sort of triangulate the position of the molecules that they're looking at. This is a PET scan of a brain on the left, a normal brain on the left, and a brain with reduced activity on the right in a patient who had Alzheimer's disease. So a lot of times they'll use these labels on sugars, and sugars will go to parts of the brain that are active because they need sugar to run, to think. And then you can see these bright spots that show the high levels of activity in the brain, or in contrast, dark spots that show lack of activity in the brain. So this one's just sort of a fun question to see, what do you guys think? Which one of these will expose you to the most ionizing radiation? We'll pause and give you a second here to answer this question. It turns out, you guys, this may surprise you, it's a banana phone. So there's actually some potassium that's radioactive, and since bananas are high in potassium, they have a significant amount of radiation. Of course, it's still a pretty small amount, totally safe to eat bananas and normal to do so. Okay, the way we measure radiation is with a Geiger counter, and it measures ionizing radiation. Ionizing radiation means that the radiation has enough energy to cause electrons to get kicked out of an atom or molecule. And in the case of a Geiger counter, it's usually argon. And so the radiation will hit the argon, and the electron gets released, and the electron creates an electric current in the Geiger counter, and we measure that with the meter. So which forms of radiation do we think are ionizing radiation? It has to have sufficient energy to remove an electron from water in order to be classified as ionizing radiation for people, and that's because we're made of mostly water. And it turns out a lot of the light that's in the world around us, radio waves, microwaves, those kinds of things that are used for communications, infrared radiation, are not ionizing. Visible radiation is not ionizing, but UV radiation, X-rays, gamma rays, are all ionizing radiation, and so are alpha, beta, and positron emission. So they have sufficient energy to remove an electron from water. That's problematic because water that's missing an electron will end up forming hydroxide radicals, and hydroxide radicals can do a lot of damage in your body. The next thing I want to talk about is penetrating power. And penetrating power has to do with how far or how deep particles can travel through your body. So alpha particles, because they're so big, can't actually penetrate your skin. Beta particles can penetrate your skin and get into superficial layers of tissue, and gamma rays can actually go all the way down into organs. And so gamma rays have the highest penetrating power, but there's something else that we have to consider as well, and that's something called the relative biological effectiveness. This has to do with how much damage it causes when it comes in contact with human tissue. So alpha particles, even though they have low penetrating power, have a very high relative biological effectiveness, the highest of these types of radiation that we might encounter. Gamma radiation, even though it has very deep penetration, has a relatively low relative biological effectiveness. So I'd like you guys to take a minute and talk to your neighbor about which type of radiation you think is the most dangerous. And you should qualify your answer. Which type would be the most dangerous externally, and which type would be the most dangerous from internally? So like if you ate it or breathed it in. So go ahead and pause and talk to your neighbor about that for a minute. And what we'll find is that alpha particles, even though they have the lowest penetrating power, they have the highest relative biological effectiveness. So in fact, alpha particles can be very dangerous if they're ingested, or they get into your lungs if you were to inhale them. Because once they're inside your body, they'll cause sort of a lot of damage to the tissue that's right there. Gamma particles, on the other hand, have the highest penetrating power. So even though they have a relatively low biological effectiveness, the penetrating power makes them the most dangerous from external sources. So let's answer this quiz real quick. We'll pause again. Beta particles is a good answer here, and that's because gamma and beta have about the same relative biological effect, but beta has less penetrating power, so it's less dangerous when it comes in contact with your tissues. Okay, for those of you who work in medicine, it can be helpful to think about the dose of radiation that you're receiving. Some of you may even have a little name tag or a badge that you have a radiation monitor, a dosimeter badge that's worn by people who work with radiation. Usually, exposures are on the order of millirem. So 5 rem is the upper limit of allowed exposure for those who are working with radioactive materials, but usually it's on the order of millirem. Rem is just a unit. We didn't talk about this, but it's just a unit that we use to measure radiation. And the reason I'm showing you this is because I want to highlight the sort of difference between long-term small doses of radiation, which tend to be not damaging as long as they're kept below 5 rem. And this is actually 5 times lower than when we start to see a detectable response. So that's why the limit is set to be purposefully conservative. But then you start to see things if you have higher exposures, like your white blood cell count goes down. You might get radiation sickness, which is vomiting and burns on your skin. You might actually have all of your white blood cells obliterated. That would be really bad. 500 rem is the LD50, so that kills 50% of people. Greater than 600 rem is generally fatal within a week or so. In fact, This is useful information to know for lots of people, but maybe especially for former Russian spies, because sometimes they get attacked by the Russian government. So this is a guy named Alexander Litvinenko, who was a Russian spy. We assume that he was assassinated by the Russian government. This is him when he was healthy, and him after he had been poisoned by polonium-210 in his tea. So he had a lethal dose of the polonium, and it was inside his body, and there was nothing they could do to save him. So he ended up dying. It turns out humans are actually not super resistant to radiation. 500 rems will kill half of the people. Bacteria are a lot more resistant, and in fact, insects are extraordinarily resistant, which is probably why there are 1.4 billion insects for each human on the planet. Good to know, right? Okay, last thing today is summary. These are our objectives for the day. So take a moment right now, look at each of these objectives, and talk to your neighbor about how you would approach these different scenarios, and go ahead and write that summary down in your notebook.